Good morning, mathematicians. Welcome to a new office hour. I think I will not be teaching. I don't think I have any official teaching duties this spring. So that might be a good time to run an online course on something through my channel. Maybe do an extra regularly scheduled stream or something. Representation theory, maybe. I don't know what. That seemed to be popular when I mentioned it before in chat. But there could be other things. My only apprehension is, like I was talking about yesterday, I don't like having any obligation. Could always do it the first thing in the mornings, I guess, back to back, instead of this. Well, not instead of the stream, but in addition to the stream. But the problem is, I also, it's good to get working right at the beginning of the day. I think it sets the tone for the rest of the day if you get up and like accomplish work immediately. So I don't know, something to keep in mind there. Okay, let's see how things are doing. Oh, I'm gonna climb the Calgary Tower again today, like I did last week, but I'm going to start earlier and let's see if I can do it more times without dying. So, wish me luck. Let's bring up Reddit, maybe. Actually, I was looking at it already. I don't know if there's any great conversation starters here. Well, I mean, there's this, but like I need to go read this article before I can say anything about it. Sounds interesting. Yeah. Math tool. Math as a tool. I don't know if there's all that much I feel inclined to discuss. Well, textbook recommendation. I might be able to talk about that. Oh, statistical theory. Math scratch to itch. Needs to be interesting. Started proper root in. Well organized but dry. Yeah. Yeah. Good morning, Edit Smith. I'm open to a variety of options, but shouldn't be too advanced as I'm rusty. Yeah, I don't know what would be a good option for someone in this position. My default thing is just recommend a Luffy to everybody. It is good for self-study. I do think it's good for self-study. Which is why I'm tempted to recommend it. But it may be, probably something lower level might be better. I don't know. But actually, interesting. Doran Zielberger. He's a pretty extreme finitist, actually. If I recall correctly. Yeah, this is the guy. He's like an extreme finitist. He thinks like we should be like all math should be done like with computers. I guess he's probably a constructivist as well. Um, oh, a bunch of interviews. Interesting. 2024 interview. I might actually check that out. Um, yeah. But he's also, I would not say he's a crank. Uh, he has strong opinions. You started to read the Quaternion book by Conway. Nice, nice. Yeah, it's a really nice book. Um, I wouldn't say I understood everything in that book, especially like in the later sections. I guess I lost focus, but the early stuff is cool. You know, the stuff about the symmetry groups and the left and right multiplication operators and the Dixon doubling process and all that stuff. Yeah, it's a fun book, definitely. It's just it's even nice to read, even if you just don't like. There's several different ways of kinds of reading math, right? You can read math. Good morning, Nicole. You can read math in a very technical way, like the best way to read math is, to have a pen and a piece of paper beside you and to, be actively like writing things out, and working with math, working through the things as you go and challenging the things and whatnot. But there's also, I do a lot of casual math reading. So, well, I mean, this is also a good skill for research, right? To do casual math reading, because sometimes you just need to extract the results from a paper. Well, that's not quite casual, but it's not quite the same as sitting down with a pencil and a piece of paper. You're also like, you're trying to extract information. It's more utilitarian is not the right word, but yeah, that's the rough idea I'm getting at. But then there's what I call like beach reading. Some people like to bring light, fluffy reading with them to the beach, but as a mathematician, I like to bring math with me to the beach. But okay, am I gonna sit there and like deeply learn the topic that I've decided to bring with me? No, definitely not. But I will bring a math book, and I will do some like light reading. It's like, okay, you don't use all your mental power deeply understanding the proofs, but you still sort of get some sense of things that are going on in the text. That being said, I mean, it's a book worth working harder to understand what they're saying as well. But it's also not written like a textbook. It reads more like a story almost. Oh, you know what? One thing is, I never talked about the other day. Do I buy math books or get them in my local library? So definitely earlier on, a lot of books in my collection were just ones that I bought myself online because I wanted them. I also, I remember one year for Christmas, my parents asked me what I want, and I put a bunch of different stuff on a list, and a bunch of textbooks on the list, and they ended up getting me sheaves in geometry and logic. But yeah, so I've spent like hundreds and hundreds of dollars on textbooks at this point in my life. Largely online, but also I worked at this bookstore for a little while, and they had a bunch of math books there. And then there was a bookstore not far. It was like just a regular kind of bookstore, not far from my undergrad campus. But I guess when professors retired, they donated their books there, or sold their books there. So I bought a lot of like cheap, little weird math books there. Sometimes there were some gems. Yeah, and so I mean, I try to look in small bookstores if there's ever like interesting used math books. I mean, that's hard to find. And then a lot of books actually I've got through the years from professors. Either just like I think my copy of Rudin, one of my profs in my undergrad just gave me his copy of Rudin. Um, Same thing I think with a copy of a group theory book that I have. I believe that was like a gift from a professor. Um, Galleon's abstract algebra. And and then of course over the years there's been lots of like, oh, this person retired, or someone that retired like 20 years ago, they finally like clean out their office and they make all the textbooks available, stuff like that. So can we talk about geometric Langlands work of Witten, Frankel? Unfortunately, not really. I don't know. I don't know a ton about geometric Langlands. Yeah, I know the very basics. But I'm much more local Langlands, and much more. I would say a 20th century perspective. In Brazil, they get super pricey. They're everywhere, I know, but our economy doesn't help. Yeah. Yeah, there was. Oh, gosh, I saw some. I might have to. Where was it? There's also sometimes there's like book sales online or something. Oh, you know what a good place to. Um, what is it? Is it Abe Books? There's some like if you look at used bookstore, um, I don't know if they I don't know if they ship to Brazil. I think this might be Canadian company. Is it Abe Books? There's other ones like this though, like Abe Books, where, um, I don't know, I don't know. Let me just type in sheaves. uh, okay, no, that's not coming up. Differential geometry. Let's see what comes up. Yeah, so look, there's a book for $11 US or 775. Well, okay, 775 shipping. So that's like, I mean, I don't know how big and long this book is, but like, that's not bad. University is partners with Springer, access to all PDFs. Yeah, yeah. I mean, you can find tons of right. Like, I've got um, untold gigabytes, probably not terabytes, but untold gigabytes of downloaded PDFs. Both, yeah, my university has access, and then there's also just so many things that are online, right? Like Alufi's such a popular book, and same with Rudin. If you just Google Alufi PDF, like it comes up. You don't have to pirate it or anything. It's just there. Alufi PDF, Rudin PDF. It's just there. Oh, let's look at the. I will maybe bring up something about geometric Langlands in a moment, but Ravi Vakil book. Yeah, look at the Rising Sea. I can't remember what the name of the painting is, but I love that choice. Princeton University Press. Yeah, this one's more expensive. This is not. I didn't bring this up as an example of a cheap book, and this one you can just get the PDF. It's freely available. $150, so maybe I want it. I really want it. Okay, there is this one book, Introduction to Langlands. Yeah, the green book here by Daniel Bump. Well, I don't know why it said by Bump. It's by a lot of people, Bump included. Did I have a digital copy? I thought I had a digital copy. Oh yeah, I wonder. Maybe I can access it if I go through my library. In China, there are cheap Springer books like GTM series English for a fraction of the price. They come with a warning on the cover that they cannot be sold outside of China. Yeah, I think I have one of those actually. I think I bought one of those online through some used bookstore for Kristen Ginsburg's book. Um, I think I probably talked about this. Well, I know I brought this book up on stream the other day. Oh, I have it open actually, but um, I've also, I think I might have talked about this one already in my book review series. This is like one of the main texts that I've had to sit with for my thesis. It's very much centered around a lot of things in this text. But I do want to find a copy of the introduction to the Langlands program. I was sure I had one downloaded already, but well, if I an introduction to the no, nothing's gonna come up. Do I have access? Sometimes I weirdly don't have access. Oh, yeah, see, oh, okay. Here's the weird thing. It only allows me to have the hard copy. Whoa. This is interesting. An informal introduction to categorical representation theory and the local geometric Langlands program. That seems interesting. Whoa. But yeah, I would recommend that green book. There is an introduction in that little green book to some like geometric local Langlands type stuff. So, oh, but maybe this is good too. It looks like there's some interesting stuff here. Yeah, I still think this is, where is it now? This is a good book. The last chapter is on, yeah, okay, so the beginning, there's like elementary theory of L functions. Also, this book is not meant to be a textbook where you actually learn these things from properly. It's like more of an overview type thing. A beach read, if you will. L functions for elliptic curves and modular forms. Tate's thesis. That's like one-dimensional Langlands. Modular forms, automorphic representations. Spectral theory, trace theory. Sort of, it ends up with the actual statement of Langlands conjectures for GLN, and then here we have the informal introduction to geometric Langlands from Gates-Gorey. So there they do talk a bit. If I recall, they talk about Bun-G and Hecke eigensheaves and stuff. Yeah. Well, let's look through these notes. These seem interesting. We got some D modules. Love to see it. Equivariance and Harishchandra D modules. Yeah, this might be a good read for me. Also, maybe for you guys, depending where you are. I don't know. I mean, there's a lot of fancy stuff here, but as an overview, as a way to get into things. Yeah. All right, well, I guess I'll download it. We'll see if I ever actually get around to reading it. Can you give us an intuition for what a D module is? Sort of. I'm actually participating in a... We're sort of trying to teach ourselves more stuff about D modules because they exist on the other side of something called the Riemann-Hilbert correspondence that our group uses. And we're trying to connect with someone who's more of a differential equations person. And so learning the D modules together might allow us to connect our algebraic skills to her differential equation skills, we hope. So a D module is basically, I guess it is some sort of object that captures a D module, captures local to global properties of some system of differential equations. That's the rough idea in an algebraic way, in a sheaf. So I'm trying to decide if I should say the full fancy definition or not, but okay, let me just write down some basic examples of D modules. So basically, you take the non-commutative ring generated by the differential. So this is sort of like the fancy word would be the sheaf of differential operators on Cn, and we need to mod out by what relation? Well, basically, we just need to think about this as like, we imagine that this is a differential operator acting on a function f. And so by the Leibniz rule, this would be f plus x del f, right? So in other words, that would be like 1 plus x del acting on f. Yeah, so basically we want these two operators to be the same, and so we basically just quotient out by that relation, right? 1 plus x del minus del x. And that sort of gives you the sort of main D mod. You can sort of think of this as defining some sort of, well, this would be like the global section. This would be like differential operators. This is like a ring of differential operators on say the complex plane. Well, I should say, let's say affine n space, affine 1 space, right? So just a copy of the complex numbers. So maybe yeah. But then normally, so this thing I've described is just a ring. It's just like the global sections. we might want to, but we're interested, it's fairly easy, as I understand. I'm not an expert in PDEs, but it's much easier to solve a PDE locally than it is to find a global solution. And so, of course, we would like to know that if I have some family of local solutions, when can I glue those together to get a global solution? And that's basically what a sheaf is, right? And so we want to consider some sort of sheafy version of this. So one normally, so we just imagine, I guess I'll avoid the technical definition for now, but D is you can sort of think of it as like D on U. It's the associated some open set is just going to be, again, the ring of differential operators, but it'll be on U as opposed to C. That's a basic idea. Yeah. Well, there's a lot more to say about D modules. What's the book I'm looking at here? The main text we're using. Actually, okay, let's go to a Char's book. I was trying to bring up the other one, which is like the main D module reference, but c'est la vie. Let's go to chapter 5. So if we look here, D modules in the Riemann-Hilbert correspondence. Yeah. Yeah, so we got a ring, ring of differential operators, and we basically sheafify that thing. Right, so here's for example, here's the example that I gave here, right? This is the global sections of the ring of differential operators. These things are also called Weyl algebras. Those are basically, the Weyl algebra is basically the algebra of global differential operators on the complex numbers. Okay, there's a lot of important things to say about them, but I'm going to skip. I have no idea why they decided to call it perverse. Well, I mentioned this. There was some stream. I think there's a stream, one of my office hours that has, I think it has perverse sheaves in the title. I think I try to explain to myself why they might have called it that, but I've absolutely no idea how close to reality that actually is. Let's see. Right, so one of the things that we're trying to study at the moment is the characteristic variety. So this is basically, okay, there's a fancier definition. It's interesting. It seems like there's a lower level, less technical way to actually compute the characteristic variety, which is, it's some subvariety of cotangent space, but most people I see, they give some like crazy definition. Well, it's only crazy to me because I haven't sat down and properly understood this natural grading. But I think there's a much easier way to actually compute it that I found in a book recently. But I just need to be sure of the theorem that computes them in both ways. But we're trying to understand those things. And then here, so here's an important part for us. So there's a special theorem called the Riemann-Hilbert correspondence that connects the algebraic D-modules and perverse sheaves in the analytic world. This is the Riemann-Hilbert correspondence. And one of the ways that we take the passage to ending up with perverse sheaves is we take this solution functor. So, okay, there's a bunch of fancy stuff going on here. Like this is a sheaf Hom, and then here we've performed some sort of like analytification of these objects. But the idea is that this should basically be some sort of complex of sheaves that encodes the solutions. Oh yeah, one thing I should have said is like more generally, you might try and define a D module. So if like this is dx on our variety, right? Dx, we might be able to write this as some sort of quotient where we have like P1 up to PR, where each of these PI is some like partial differential equation. For example, like in this original one, right? We wanted to make sure that this thing actually acted like the normal differential operator. So we wanted to force the solution, like we wanted this differential equation to hold, basically, right? But you could also imagine that maybe you ask, like, if you wanted a solution to some other differential equation, like this, or something, right? For example, well, then you would set like one of these p's would just be this expression, and then you're looking to like solve that expression, so you would put it in there, and then in some way this solution functor should be capturing that. There's even, well, do I want to explain this exercise, why that captures it? No, but you know what? I should probably do that exercise in more detail for myself. Yeah. So that's a little bit about D modules. If people don't have more questions, maybe I'll rant more about where they originally came from. So, sorry, not where they originally came from, but the origins of why they're useful for me, why they're important in my life. So, if we want to understand representations of some complex Lie group, one way we can do it is by instead understanding the Lie algebra representations of its Lie algebra. And in turn, there's a very closely, good morning, Jens. There's a very closely related, there's a special algebra related to the Lie algebra called the universal enveloping algebra. And one thing that's interesting about the universal enveloping algebra is this can actually be interpreted. I'm done. I'm cooked. I'm cooked, gang. It's over for me. We can think of this ring as a ring of, well, so there's various equivalent definitions of the Lie algebra. There's sort of a natural way to identify it, like the sort of main definition is as the tangent space to the identity of G, but we can also think about it as left invariant vector fields on G, and there's sort of a nice way to pass between all of these. Good morning, John Doe. And so this I think, in fact, I'm tempted to even say we should think of the universal enveloping algebra as left invariant differential operators. But in any case, the point still stands. We think of this as some larger ring of differential operators. And so what one can do then is like the study of, one can go back and forth, just like as one can do here, between the study of modules, like, Lie algebra representations of G and modules over this ring. And in particular, well, this ring, there's one piece of the doing a course in Jordan algebras. I know nothing about Jordan algebras, to be honest. It's been weird to try and make a parallel with the theory of Lie algebras. Yeah, I don't know much about Jordan algebras, to be honest. But now, so what one can do, so we want to study modules over here. And there's one piece, there's some part I'm missing, but well, there's a special subgroup of these groups called the Borel subgroup. So if one way to write it, I mean, there's a whole rich theory of this, and there's actually a lot of interesting and important ways to think about the Borel, so I'm going to undersell it here. But just really concretely, if you're GLN, well, really, if you're like any matrix group, the Borel is just going to be the upper triangular matrices in that group. So it'll either be in here, or you like intersect it with your smaller matrix group. Hey, good morning, Russell. And so what one can do actually is, it turns out that in fact these UG modules descend actually to sheaves on G mod B, or rather to D modules. So by going from ordinary modules on G, one can go to one can pass over to UG modules, and from there one can then produce D modules on G mod B. So somehow representations of your Lie algebra, or modules over your this ring of differential operators, should correspond to D modules, which are, I didn't properly define, okay, I mean, my plan wasn't to properly define D modules, but I should have said something a little bit more. So the D module is not itself just this ring, but in the same way that we have, like, there's OX modules, like on a variety. So what is that? That's like you have a sheaf on your variety, and like this is your like ring of functions on the variety, right? And so for each open set, that ring of functions should act on this, should turn this into a module in some way that's compatible with like continuity and restriction maps and all that stuff. So in the same way, what a D module is it's basically just, we take the sheaf of differential operators, and now for each open set, your D module is like a module with respect to this ring of differential operators. I should have said that, yeah. So we go from G modules over to modules over this ring of differential operators, and that in turn can be interpreted as D modules. So now that's really like a whole sheaf of modules over this ring of differential operators on G mod B. And then finally, one plugs in the Riemann-Hilbert correspondence to get perverse sheaves on G mod B. Who cares? What am I talking about? What's the point of all of this? Well, the point is sort of the original Kazhdan-Lusztig hypothesis. The original Kazhdan-Lusztig hypothesis. It predicted that well, basically, it predicted that the multiplicity of irreducible G representations in sort of special ones called Fermat modules. So we'll talk about, maybe I can talk about that on stream in the nearish future. But these are just sort of like larger ones that you can naturally build out of the root system of your Lie algebra. The multiplicity of irreducible representations in Fermat modules can be computed in terms of perverse sheaves on G mod B. And so the way that this happens is exactly by going through this process. So this is sort of like, yeah, this is like geometric representation theory. Like, one is starting with an interest rather of even just understanding representations of some complex Lie group, and then going into G modules, going over to UG modules, well, and ultimately, at the end of the day, you end up working with perverse sheaves on G mod B. Okay. Nerdy Quagsire, I'll address that question in just a second. But so one of the things that came out of this is the atlas of Lie groups. So there was like a big breakthrough in our understanding. What? Can't be reached. Why? Por qué? Warum? Warum nicht? Let's try here. Yeah, the atlas of Lie groups and representations. I don't know if this is new anymore. This is. I mean, this was sort of the big breakthrough of this whole project. Was computing Kazhdan-Lusztig polynomials for the group E8. It's my understanding that actually this was a big breakthrough for us in our understanding of the group E8 in general. So yeah, there's this is kind of the upshot of all of this crazy stuff, you know. So probably half of your brains melted while I was talking about all of this stuff, and it's like, why did we take representations and turn them into these very complicated things being perverse sheaves on G mod B? Like, why? Well, actually, there is a big upshot, and that is there are, even though there's a certain amount of abstraction, there's stuff about the theory of perverse sheaves on G mod B that's highly computable in a way that's just not obviously computable for representations of your original Lie group G. and case in point is this Atlas project. So yeah. Okay. First year math student, Canadian institution, interested in doing undergraduate research, but have very limited math background. How do you do research? Well, I mean, you're going to do research under the supervision of someone. So, that I would recommend if you're interested in doing research. It might be too late for this summer because probably research positions have already been filled. But what you're going to want to do is basically the way for you to get started while you're in your undergrad is just approach professors. I mean, okay, I say it might be too late. Go ahead and ask them anyways. But yeah, ask your professors if there's any research positions available. I don't know. Not all universities seem to be as like active and proactive and have a vibrant like undergrad math club, but at my university, certainly the undergrads are very active, and so every year they have a research night. So there's sort of a information session about doing summer research. So I don't know if there's something like that. But you can definitely, yeah, and your university may have its own like policy or procedure about how to go about applying to do research with someone. So I would go look into that. Ask, yeah, I don't know, whichever professor you're most friendly with at the moment, I would go ask them about what steps to take in order to make that happen. But also, one thing you might want to do ahead of time, if you're trying to approach a particular professor, like even if you don't know where to start, I would just go look at the professors. Well, you're scared of your professors. Well, yeah, I don't know what to say about that. Maybe I wasn't. I don't think I was scared enough of my professors. I just would brazenly walk into their offices at all times of day and barge in, asking really stupid questions all the time. So unfortunately, I don't have a good. I don't have a good solution for you there. But they're just people. They're just people. I don't think you should be scared of them. Yeah. So just go talk to them. That's it. You need to do it. You need to go talk to your professors. You need to build a relationship with your professors. So that's why I say everyone should go to their office hours, even if you don't need office hours, if you don't need help. What you will need at some point in your life is letters of recommendation and or someone to supervise your research. And you need to actually know people to do that. So even if you don't need help, go to your office hours and ask them interesting questions. Try emailing them first. Yeah, you could send them an email first. But yeah, I would definitely, like, what I would do is I would look at people in your department, look at what their research is in. You probably won't understand anything at all, but go look at their papers, go look at their abstracts, get the general idea of what it's about or what area it's in. Learn a little bit about that area, even if it's just like an overview of the kind of things that they work on, just so you can be able to be like, hey, I'm kind of interested in this area. I heard about this thing and that thing. I don't know much about it, but it seems cool to me, because, yeah. Don't try and BS them that you actually know what you're talking about, because they know you don't. But know enough about the area as an overview so you can say some words that show that you've actually like looked into it and you've taken an interest, right? So that's that's what I would do. Like don't just send them an email. Like, yeah. Yeah, you should get a sense of, like, think about what your favorite math classes were, and that's something too you can toss in. You could be like, oh, I really liked algebra, and so therefore blah blah blah. Um, yeah, yeah. But you did say you have a limited math background, so that, I mean, that might make it a bit more difficult for you. But here's also something you could do, because this summer it might be too late. You can sort of play the long game, and you can go to one of these professors and you could say something like this. You could say, hey, I would be interested in doing research possibly next summer. I'm interested in your area. What are some things I could learn over the next year that might help with that? And you could ask them for like a textbook recommendation or something, right? And then that gives you a way to keep that channel open, right? That'll show them that you're interested, and then seriously take up that study over the next year. Try reading that book a bit. On your own, and then that also gives you an excuse to go talk to them more, right? That opens up a channel of communication. You could ask them, hey, do you mind if I swing by and I ask you a couple questions? I'm sort of struggling with this reading a bit or something, right? And then that'll like sort of help build the relationship between you and the professor. And then, yeah, even if for whatever reason the research there doesn't pan out, which hopefully it should, because I think that would speak volumes if you spent a whole year trying to like dig in and learn this book. But it may be that you have a lot of catching up to do. But then that's also what you might do is. That'll just help build the relationship with the professor as well. The one grad student at your school told you to read Alufi. Yeah. Was it me? You said Canadian institution. Was it me? Yeah, I mean, read Alufi. Yeah, if you're interested in algebra, for sure, read Alufi. It's a really good book for self-study. In general, math research is highly specialized, though, especially to other domains. How realistic do you think it is to have undergraduate research in math? Super realistic. I have a research paper for my undergrad. Now it was me. Okay, nice. But I have a research paper from my undergrad, and it was in graph theory, which, is maybe a bit easier to write, to find projects there that an undergrad can do versus like an older and deeper topic. I mean, again, I want to be careful here, not to say, I mean, there's like very deep, hard problems in graph theory and very talented graph theorists. But generally speaking, the field has also a lot more readily accessible things that one could get into. So I actually do have some videos. I think I have some older videos on my channel about the gluing lemma. Yeah, if you look up like the gluing lemma, there's some old videos of mine. I don't think I finished it actually, but I started explaining my undergrad research. I don't know where it is, but and also here the other thing too is like a lot of summer research projects won't end up in papers, right? But like the prof will still, I don't know, professors will still, like, at the very least, you'll learn something. You'll just sort of learn something extra. But there is also tons of, like, there's lots of stuff to be done out there. And yeah, maybe what you do in your Actually, I mean, yeah, every field might have some little thing, right? Or like a professor might have some tiny little tidbit that they can try and teach you to so that you understand enough to work on. Yeah, majority of undergraduate research these days is in combinatorics. Yeah, just because there's a lot more directly accessible things that can be done in combinatorics, right? Like something fancier like algebraic geometry. I mean, it just takes more time to get up to speed to the way that things are being done now. That yeah, it's just not as realistic for an undergrad to do that. But you can still cut your teeth on some combinatorics, even if you're interested in other things, right? It's still research experience, and but even then, like I've known like there's undergrads that have done projects in all sorts of different branches, and they bite off a little tidbit and they make some little contribution. And yeah, is it going to be the same kind of thing that you are like proud to put on your CV as a postdoc researcher? No, probably not. But yeah, it's still experience. So graph theory, combinatorics. Perhaps these require less background to get into research questions. Yeah, generally speaking, yes. Do I have any experience with complex geometry? Very into algebraic geometry, but not sure if I want to go to the arithmetic or complex algebro-geometric route. Yeah, I have experience in complex geometry. Like my master's thesis was basically about complex differential geometry. I do a fair amount of complex differential geometry now. Yeah. I would just say keep exploring all of it. Yeah, at this point, I mean, I don't know where you are in your career, but I would just, I mean, if you like geometry, you like algebraic geometry, then I would just cast a wide net. Learn. I mean, there's like cool stuff that's even at the intersection of all of these ideas, right? So part of my master's thesis was about the arithmetic. I actually didn't understand this part at all. This is sort of the background stuff that was like the reason why my master's thesis mattered. But the arithmetic Siegel-Vey formula, and basically the idea is that you study some sort of like arithmetic curve. So we're interested in like this is like a number field, and like this is and this is some sort of curve. Oh, another keyword here is Arakelov geometry, right? So we're interested in these like arithmetic curves over some field, and so from this, there's sort of, you get from the like the non-Archimedean places, you get some sort of like p-adic curve theory, but then also from the Archimedean places, you get these like Hermitian. You end up studying things like Hermitian vector bundles over the complex points of your curve. And so there's kind of this whole merging of like arithmetic geometry and complex geometry stuff. So like there's cool things you could look into with that maybe. But I would just say keep studying both differential algebraic geometry, maybe look into some number theory stuff if you're interested in arithmetic. And I think it's good to have a wide a variety of interests, pun intended, because then that just gives you more options for grad school. Like you'll there's more places you'd be happy ending up. So yeah. Surely the ultimate undergraduate research project would be graph theory combinatorics. Bachelor's, currently studying, reading course with a postdoc. Nice. To soon start cohomology of sheaves. Awesome. That sounds great. That sounds great. Yeah. Yeah. So just keep digging into that and just follow what you find most interesting. Spinors are widely used in modern particle physics. Have I looked into the formalization behind them? Yes. Like a million years ago, I've looked into it. I can't say much about it. And my coffee is basically done, so time to go proof theorems. Is that time of day? Proofreading time, proof thinking time, proofreading time. Everything with